Good morning, everyone. Thank you, Mr. Chairman, for your introduction. My name is Manuel Bermudez, and it's an honor for me to present the research that we have been conducting along with Professor Hong at National Cheng University under the title Fiber Distribution in UHPC Beams. And today I'm going to present mainly an insight from 3D micro-CT scans on shear tests. So the main question would be, does the beam's depth impact the fiber distribution characteristics in UHPC beams? So for this, we developed a series of 5 tests. We have 5 beams with beam with a smallest effective depth of 250 millimeters. The beam with largest effective depth has 1,000 millimeters. All these beams have the same fiber reinforcement. They were all casted at the end of the beam, and they are having all the same reinforcement ratio, and they all had 3-point bending for shear tests. They all had shear failure. So here I'm showing a free body diagram of forces acting along the inclined shear crack. The line XYZ represents the inclined shear crack, and we are assuming that when we have fibers, we're going to have some contribution along the inclined shear crack. How much is the contribution? That's still an open question. So what we decided to do is to extract some cores to generate some micro-CT scans and then figure out what is happening inside and do a forensic analysis to understand, qualitatively at least, at this stage, how much is the contribution of fiber reinforcement. To obtain drill cores from UHPC I-shaped beams, we obtained 3 cores from the web, one from the top of the web, one from the middle of the web, and the other from the bottom of the web, and we obtained one from the flange. Also, to obtain from the flange, it's not that simple because we had to extract one from the horizontal direction, which is the one that we are analyzing, and then we extract one from the vertical direction. We drill another hole from the vertical direction to extract the horizontal core. To be honest, there are some issues with drilling cores in the longitudinal direction of UHPC beams. So it's really easy to drill a 150 millimeter long core. What is really hard, is almost impossible, is to extract the core due to the fibers in the core end. So therefore, in this study, we only have from the transfer direction. So when we prepared the UHPC core samples for the micro-CT scans, I'm showing here a figure where you can see the core from the web and the core from the flange. Usually, we remove 3 times the length of the fibers in the core end, just because we want to eliminate the wall effect. And this is, in this figure, I'm showing the sample that we're using and also the core ends that we are eliminating and we're not using for this study. Just to give you an idea, if you consider how much fibers are in that small core, there will be like 1,657 fibers. If you align them linearly, there will be 21.5 meters of fibers. That's just a lot of fibers. So, of course, counting fibers is not a simple work, but it's part of what we're doing right now. So here is just showing the setup that we're used for the micro-CT scan. And I'm here showing the 3D volume distribution of the micro-CT scan images. These are the properties of the machine that we were using. And you can see the XY axis with respect to the beam. So in here, I'm showing a figure where you have 3 cores. One has 0.75% fibers. The other has 1.5% fibers, and the other one has 3% fibers. And you can see the low porosity that UHPC has. You also can see how the fibers, depending on the fiber volume that you're using, how they distribute in these cores. So we're going to do some qualitative analysis of the fiber distribution on shear tests of UHPC beams. And for that goal, we had 4 beams initially. So the first beam that had the smallest effective depth had effective depth total of 250 millimeters. The largest had effective depth of 1,000 millimeters. And then they all have the same reinforcement ratio. They are all using the same fiber volume fraction of 1.5%. So we obtain from the shear crack, where the shear crack originated, we obtained the cores. And you can see that we are obtaining cores from the top flange, from the web top, from web middle, and the web bottom. And the reason why we do that is because we want to get the shear resisting area and understand how's the fiber distribution in the shear resisting area. And we don't obtain anything from the flange because it's from the top bottom flange one, because it's almost impossible to cross all those rebars, and the second one is because we don't need it in theory for shear. So in this figure, I'm showing the CT scans that were done for the beam that has 250 millimeters, and then in here I'm showing the scans of the beams that had 500 millimeters effective depth, 750 millimeters effective depth, and 1,000 millimeters effective depth. All these beams have the same fiber volume fraction, and we can see that there are differences on how fibers distribute. But to understand a little bit more these figures, we generated a table to have an orientation category. And this category allows us to understand what's the range of inclination of the angles depending on what we observe in the figures. And we generated 4 categories, one being random, partially preferred, and then preferred. And when we analyze these figures based on these categories, we found out that the beams that had effective depth of 250 millimeters had a random and partially random orientation. And as we increase the height of the effective depth of the beam, we see that the web middle and the web bottom are starting to get preferred orientation or partially preferred. And I'm telling this is still the web shearing, the shear resisting area. This is not the bottom flange. So if you have fibers that are oriented almost horizontal to the shear crack, then that changes a little bit how we design shear tests for UHPC beams. We have another analysis done for different volume fractions. In this figure, I'm showing two beams, the one that has 1.5% volume fraction, and the other has 0.75% volume fraction. All the other parameters are the same. So in here, we are observing the beam that has the cores from the beam that had 1.5% fiber volume fraction, and then here we observe what happens when we reduce the fiber volume fraction to 0.75%. And if you remember the beam that has 250 millimeters effective depth, we're getting almost the same random and partially random distribution in this beam. So doing again the same analysis on the orientation category, we find out that we have the beam that has 1.5% fiber volume fraction has preferred and partially preferred in the web bottom and the web middle, and in the top flange and the web top we have random and partially random. While when we reduce the fiber volume fraction to 0.75, we get random and partially random orientation. There are some implications of the fiber distribution and shear strength on UHPC beams. One of these will be fiber efficiency varies along the inclined shear crack of UHPC. So if you have a beam that has 250 millimeters, we're going to have some random orientation along the inclined shear crack, telling us that beams with this effective depths of 250 millimeters have the same fiber efficiency along the inclined shear crack. While if we increase the height of this beam to get 1,000 millimeters, we're going to have, as I showed before, some random and partially random orientations in the web top and the web flange. But if you keep going down, you're going to have some preferred or partially preferred orientation, telling us that the fiber efficiency varies along the shear crack in beams that have 1,000 millimeters of height. And then the fiber distribution effect has a higher impact orientation as the beam's depth increase. So when we're pouring concrete, and if you have a beam of 250 millimeters, you're going to have pretty much random orientation along the beam, telling us that there is no fiber distribution effect noticed at this height of the beam. So we're going to probably get a random orientation in this beam. Now, if we have a beam that has 1,000 millimeters and we start pouring, initially we're going to have also some random orientation. But as we keep pouring, then the profile of the fibers change. Then we're going to have the random, partially random, and partially preferred and preferred in the bottom of the beam, telling us that the fibers that were decanted from the upper layers of UHPC modify the fiber orientation, leading to the majority of the fibers in the lower layers to incline at angles between 0 and 15 degrees with respect to the X and Y plane. And also, as the layers of UHPC steps are increased, then we have lower fiber content. Finally, considering the anisotropy of UHPC, is it reliable to use the tensile strength as the main beam shear predictor? So currently, for predicting shear, you have to report in the tensile strength of UHPC, we usually have two tests. One will be the direct tensile test, either using a dog bone or a prism, and then we're going to have an indirect tensile test using inverse analysis on a flexural beam. However, with our study, we're proving that there are three issues that probably these two tests are not able to capture. One is fiber efficiency along the shear crack, fiber distribution effect, and the varying fiber orientation along the inclined shear crack. Therefore, we have taken a different approach, which is by modifying a fiber factor for UHPC. This fiber factor was originally derived by Naman using a probabilistic model. We have proved that this fiber factor can work for hybrid fibers or for monofibers, and we are limiting the fiber efficiency to 41%. And then we obtain an equation that was optimized using 118 HS and HPFRC and UHPC non-prestressed beams, and we consider that this equation has the size effect of ACI 318, and also we have considered a shape factor that considers if you have flanges in the beam. In here, I'm showing the predictions that we can obtain using this equation for these 5 beams that we tested in this study, and we can observe that pretty much the equations are predicting very accurately, except for the beam that has 1,000, and that's a question, an open question of is the size effect factor working for these beams? Maybe not, but that's still an open question, a different open question. And then we can also extend this equation for pre-stressed beams by adding this factor that I'm showing on the slide. And we can see that from these 7 beams that were taken from the literature, these beams have no stirrups. They are pre-stressed but without stirrups. We can see that the predictions are pretty reasonable. And it's interesting to note that in these studies that the sets of beams that we chose, they have effective depth of 305 and 821 millimeters, showing that our equation can advance the state of the art of shear strength of UHPC. And that's all from my side, and thank you for your attention.